Okay, great. Well, thanks for the great introduction, Donica, and thanks for having me here today to talk to you all. It's great to meet lots of astronomy enthusiasts. Thanks for being more of them around. So yeah, as Donica said, my research, I'm a PhD student here in UCD, and well, just downstairs. I'm part of the star formation group, and my research focuses on protoplanetary disks. But I was also lucky enough to be part of the AirStar1 team, so my talk will be kind of split into two parts. On that, I don't know the general structure of questions or not. I'm happy to take them during the talk. If I gloss over something or something's not clear, just shout at me on Zoom or in person, whichever. I don't mind at all. So yeah, as I said, I'll be talking to you about rings of promise, protoplanetary disks, and a little bit about the AirStar1 story and the more or less end of that. So yeah, as I said, the talk will take kind of two parts, and my aim is to kind of give you a bit of an introduction to the field of protoplanetary disks and the kind of star formation and kind of ongoing questions that we have in the field today, and what my research tries to do. And then, as I said, with the AirStar1 story, a bit of a recap, and then a story of its lifetime, and then a kind of end of mission facts. So, making the talk, I came up with the name. Thank you. Rings of Promise. Now, when I was talking to Antonio Martin Carrillo downstairs, he was slightly slagging, giving off on me, saying, "Should have called it. If you like it, put a ring on it." So, you know. This is why he's good at this kind of stuff. So apologies for that, but I had to put it plugged in. But yeah, I like the name Rings of Promise because I mean generally these disks are kind of like rings, and it's kind of promise not in the sense that it's guaranteed a result, but a lot of potential that can happen, a lot of potential for interesting things to happen in these objects. And so I hope I can convince you to agree with me on that in this talk. So if you want to boil down to something really simple, we can compare it to like a Friday. It has two simple parts. A young star at its center, or the egg yolk, and a disk of gas and dust surrounding it, like an egg white. And that's kind of about it when it comes to similarity between the two things, because in reality they're a lot more complicated. So what you see here on the right-hand side is an image of a famous object called HL Tau in the Taurus star-forming region. It's a protoplanetary disk that's 450 light years away, so that's translated to around 21 billion, 4.5 trillion kilometers away. And it's one of the most famous ones in our field because quite beautiful to look at, and there's a lot of things interesting about it. So you can see in the center of this image the hot young star, and then around it this disk of gas and dust, and these intricate features of rings and gaps in the disk. So, as I say, all these systems come down to two parts. The center of it is this baby star. It's still evolving star. So, kind of when I say that, it's still maturing, because when we talk about the lifetime of stars, to the point that they reach would be called the main sequence, and at this point the star spends most of its lifetime, and like our sun is currently in that state at the moment, and it kind of reaches that point at around, we say, between 10 and 20 million years old. So protoplanetary disks are these still evolving stars that are younger than this this point. So the star is still evolving, it's still growing, there's still chemical processes going in at its core, and it's still interacting with the material around it, and that makes it quite dynamical and quite exciting, because there's lots to look at, a lot of things that we don't quite understand about. And then the other part, the egg white in the fried egg, is the surrounding disk, which is composed of gas and dust. And you're going to hear me say gas and dust a lot in this talk, because where a lot of the research comes from, and it's really what we can see in many cases from these disks. Now, in terms of mass, of the disk alone, we have around 1% of it is dust, and the remaining 99% is gas. However, the dust, although it's only 1% mass, is really important because it's largely through the dust that we see these features, because it's the dust grains absorbing light from the star and re-radiating or reflecting it out for us to see. And this disk surrounding the star is bound by the gravity of the central star, and it swirls around and orbits it as the star develops. And over time, eventually, this disk tends to dissipate, and we're left with what we hope to be a planetary system. So to give you a size of scale, this disk, HL tau, has an approximate measurement of its radius to be around 140 astronomical units. So one astronomical unit, it's a unit of measurement that we use kind of in the scale of solar systems and kind of within our galaxy. It's the same distance as Earth is to its sun. So it's 140 times that. And just for comparison, our current solar system, Neptune, is around 30 astronomical units away from our sun. So this is, quite a bit bigger than that. And if you want to put that in terms of kilometers, that's around 140 AU, around 21 billion kilometers. So they're quite big. And as I say, because these things change over time, its mass and how big these disks are really fluctuates because of the interactions with the star and then interactions with the dust and gas itself as it evolves. And the thing that we like, why we're particularly interested in them, is because it's, as the name protoplanetary disks, is they're kind of nurseries of planet formation. So it's in these disks that we believe we see planets starting to form and that eventually go on to make solar systems like our own. So in a summary, if you were to put it into a dating profile, what these things would have, you can see HL tau, 5 million years old. Its disk, or its bio might say, full of life, looking to grow and develop. Love spending time with very close, gravitationally bound friends of gas and dust. Curvy in all the right places with hundreds of astronomical units in radius. Don't ask about the weight because it's constantly changing. Love to be active and social, and looking for the right partner or conditions to hopefully have kids or protoplanets someday. And it's around 4.5 trillion kilometers away. So I know I was quite right. I don't know about the rest of you, but we'll come back to that. So this is just a little video that I have to kind of. It's not an image of a real system, but it's a simulation just to kind of get a sense of what it really look like. So you see here at the center of this, we have our still evolving star, and then this disk of gas and dust orbiting around the star. And you have features like these gaps and these rings. And then slowly over time, as the star continues to grow and feed on this material, this disk of gas and dust starts to slowly fade away and dissipate. And as it gets older, we believe and we hope that you start to see these planets forming in these gaps. And they also then feed on this material from the disk. And then eventually, as the star gets older, coming up to this 20 million year age mark, we start to reach the main sequence and starts to mature into kind of an adult star. And at this point, the disk has generally gone away or disappeared. So it counts as a bit of an illustration as to kind of how to think about these things. So my dad's a civil servant, so he does work that is actually important. And he generally comes to me and says, why the hell should we care about these things? So first of all, as I said, like in the name, these are what we believe to be the birth sites of planets. And you can see an image here on the right-hand side of another famous system called PDS 70. At the center, you have this evolving star, and then you can see clearly the bright ring around it. But the little blob in the zoom-in part, what that is, that was a detection of a planet. And this is the first and only system to date that we have seen a planet actually forming in the disk, kind of in real time, if you will. And then follow-up studies on this, because this became a big hot topic in the field, this object. We then seem to find 3 and potentially 4 planets in the same system. So really showing that these can evolve into planetary systems like our own. So that's one thing, because one of the many open questions in astronomy in general is how do we form our planet? How do we get to this point? So understanding the way these disks evolve and change over time is really key to understanding that. And then, as I say, we'll go on to planetary systems, which potentially might harbor life or have other important features in them. But it's not just about the planets, it's also about the star, because as I say, the star is still growing and developing, and there's lots of open questions on that and what's going on there. So again, as this is an important question, is looking at these objects as a way of understanding the star at its center. And then furthermore, in the disk itself, as I say, if we go to form planets, we have to go from the start point where we have these tiny little dust particles to eventually forming planets. So there's a process of chemical and structural evolution for these dust grains to go from something really small to a planet, and then also in the same way the gas changes and evolves into creating more complex molecules, and again things that we need to enrich the space, the interstellar medium, but also what we need to make planets and stuff. I don't know. Okay. And also, I think they're cool. And if something's cool, I don't see why not. Why you shouldn't study it. But I don't think Zoom wants me to. The other reason I think we should care is they're really pretty. So this is an array of images taken in scattered light of different protoplanetary disks. I wanted to show you this because you can see the range of features that we see here. These are all protoplanetary disks. These are all these are all in this stage of their life. But you can see a huge variety of shapes and structures. They don't all look like the picture I showed you before. So you have some like this that have these spiral arms in it. You have ones with the rings, like the one on the top right. You have some like disk symmetries here, and then some messes like this that, who knows what. And all these features come from different ways in which the star interacts with the disk and everything that's going on there. So there's really a lot to look at because each one tells its own story and each one feeds different information to us about this evolutionary process that we're looking at. So the other thing too that's important to know is how these things form. How do we get to the point of having a protoplanetary disk? So, kind of famous saying that we're all made of stardust applies in a lot of cases, and it's the case here. We kind of start our story with these huge clouds in interstellar space called molecular clouds, and once again they're full of gas and dust, but they're huge. They're very dispersed. You can see here the scale here is 20,000 astronomical units, so massive compared to our disk that I showed in the previous one, which was 140. And eventually, over time, this big cloud of gas and dust you start to have particles start to become gravitationally bound to each other, and they start to kind of clump. And eventually, once this reaches a certain criteria, this clump, the gravity starts to dominate, and the whole cloud begins to collapse in on itself. And at the center of this collapse is the seeds or the first starts of a star being born. And it can be one star or it can be multiple stars at the center of this. But also, as this happens, the center of this collapse begins to rotate. And what happens is as it rotates, as it collapses, this rotation continues to happen, and eventually you're kind of flattened out into a disk, kind of like if you were rolling dough or something like that while you were baking. And this tends to happen over quite short time scale relatively to the rest of the process. But once this collapse begins to complete, what you're left with is this stage. It's not quite a protoplanetary disk yet, but you start to see the resemblings of this star at the center, and you can start to see some kind of a disk around it. But you still have this infalling material coming around it, this protostellar envelope. So this is the remnants of the cloud. And then you have these really dramatic outflows. They can be jets or winds that spew incredible amounts of material back into space, and that comes from the magnetic fields of the star, and as it starts to come to terms with its own power in a way. And you can see already how the size scale changes. We go from 20,000 astronomical units to 500 in this stage. So all this matter starts to become really condensed into a relatively small space. Eventually, this then comes into the protoplanetary disk phase, as the picture that I was showing you. Now, the star is still evolving, as I said. It's not quite as dramatic as the previous stage with outflows and stuff, but there's still a lot going on, which I'll come to next. It's still interacting with the disk. You still have lots of magnetic fields. Magnetic fields are the bane of our study. We like to call it black magic because we don't know what's going on. But yeah, and at this stage, as I say, everything before this happens in around 1 million years. But then in the protoplanetary disk phase, we go from around 1 to 10 to 20 million years before it moves on to the final stage, which is that of the planetary system, or so we hope. And again, notice how the scale changes from 20,000 AU, 500, 50, and then eventually into what our solar system is like. So if you wanted to summarize that like a child growing up, you could start molecular cloud as like the pregnancy with the fetus of the star in the center, still growing, and then eventually you have the next stage, kind of the spoiled toddler phase, throwing tantrums and throwing jets and winds and being all dramatic, but still growing, and that, then you move on to the protoplanetary disk phase, which is kind of like a teenager, still, it's not throwing tantrums, but still a lot sizzling, still a lot going on. It's starting to resemble a human or an adult, and then eventually we go on to the young adult or the adult stage of the star's life, where it spends most of its time. So it's a bit of a kind of summary of that.
Can I ask one?
Yeah.
Just a very big question. Is it guaranteed then from this that planets will always form when a star forms, or can a star go through the process without actually having the planetary disk? Or
well, that's kind of one of the open questions, because as you alluded to in your introduction, we've detected thousands and thousands of exoplanets in different parts in space, but we haven't really seen how they form. So we believe it to be the case that they come from these disks, but as is the problem with astronomy, because things take so long relatively to us, we only get snapshots of it. So what we try to do is try and put these different pieces together and try and make a timeline. So yes, we believe them to eventually form planets, but I think it wouldn't be every single system that makes a planet, because the conditions have to be right. It also depends on its neighboring systems and where it's located in the galaxy and stuff like that. So it's not a guarantee, but we do think planets are forming in these disks. So yes, as I said, during this process, lots can happen. As I said, when we start off early, we have the collapse of the cloud due to gravitational interactions, and that has thrown complexity of physics in it, and do lots of simulations trying to understand that. Then you have the spinning and the production of this disk of material. But then you also have what we call accretion of disk material. So this is when you have material from the inner region of the disk that falls onto the star at its center. And when it falls onto the star, it creates these big shocks on the surface of the star, and that makes the star brighten and dim and act in all sorts of crazy ways. And this is in part due to the magnetic field of the star itself, which also produces these dark patches, which we still see in our sun today, and in a similar mechanism. Sorry, that's question. Right. Well, the chemical composition of protoplanetary disks predicts what type of exoplanets will form later on. Yeah, so that's a good question. Again, it's kind of the same. It alludes to the same issue where we want to try and understand that. But yes, ultimately, the conditions or the chemical components of the disk is what will form the planet. And so the way in which they interact and evolve over time will affect the composition of the planet itself. But it's not just the composition of the disk. You can also have the type of star you have, or how close the material is to the star. That affects its composition as well. But yeah, to answer your question, yes, that would be right.
Aaron, just one other question for you.
Yeah.
At what stage in this life cycle does nuclear fusion in the star start?
Excellent question. So nuclear fusion is the starting point when we say it has reached its main sequence. So nuclear fusion has not occurred at any point yet.
Right.
This is why the star is still evolving. You're still coming up to the point where the conditions are right for fusion to start at the start.
Okay.
And this main sequence, this where it spends most of its life, that's the point at which nuclear fusion starts. So in around this 10 to 20 million year mark.
Okay.
So we don't have it yet in any of these.
Well, what's the if you have a 50 AU diameter, and it's all gas and dust? Well, why does it have to be in the center that the ignition has to happen? It could happen anywhere in the 550 light year space.
No,
That's for all the masses.
it's for all the masses.
So then all the gas and dust has gone to the center, but it hasn't ignited to form a star.
Well, yes, in a way, yeah. So it's kind of the symmetry of the system. So if you imagine this big cloud, this molecular cloud, as I had a couple of slides ago, the pregnancy one here. If this, just generally with the symmetry of the system and the way these particles interact, the collapse will come in on itself from all sorts of directions and focus it onto the center. But at the center you have the star, but that doesn't take up all the gas and dust in this cloud. The rest of it, as I say, goes into this disk as it rotates and gets dissipated.
But the star is only 1 million kilometers wide. So the center of the disk something is have to ignite in 1 million kilometers in the center of that disk.
Yeah, the baby star, yes. Yeah.
So what is the difference between gas and dust and ignition?
The density in the middle is huge compared to the rest of it. So that's what the difference is.
Yeah.
Tom?
Yeah, so this thing called accretion that we have going on. That's one thing that we like to study in these systems, where this material falls onto the star and it creates a lot of interesting features that we see. Another thing is, as I mentioned in this spoils. Oh dear. No.
I wouldn't mind about that.
It's not a quick presentation or anything. The least of all. Yeah. So, as I said, in the spoils toddler phase, when we have these dramatic outflows, these massive jets, they are very interesting on their own. So this is a picture of a very famous one called HH211. This image was taken by the James Webb Space Telescope, and what you can see here is this. You can't see it, but at the center of that, the dark patches, is this star and disk system. But these massive plumes coming out either side is a highly energetic jet that's spewing incredible amounts of this material out into space at speeds of 80 to 100 kilometers a second. And just to give you a scale of this jet measures around 9.5 trillion kilometers long, and this is how energetic these jets are. And you can see the incredible detail in this image, all these kind of knots and shock fronts and features within the jet that we can see. So again, another kind of variety of things.
Are they polar or equatorial?
Polar.
Oh,
yeah. And then, as I mentioned before, you have over time you have the dust grains and gas that evolve as the disk itself evolves, and this begins to create new molecules that we need for life, for example, but also for other types of astronomical objects to form. And this is a little video that kind of visualizes that. So you can see the star and the disk, but if we start to zoom in, you see the dust. There we go. You see the dust particles orbiting around the star, and over time, due to various different forces, they start to interact with themselves and with the radiation from the star, and they start to interact with themselves. They mix, they collide, they can turn into ices, they can turn into methane, they can turn into different chemical structures, which is quite important. And then as well, we have various substructures in the disk. So that array of images I showed you before with these spiral arms and stuff, that comes from the dust warping and changing in shape that we have as well. So basically, I wanted to convey here is a lot can happen in these things. There's a lot of things to look at. So how do we see these things? Well, as we know, in like other sciences, we don't have a lab that we can go to in astronomy, so we have to use telescopes, and we point these telescopes at these objects to try to gain as much light or radiation from these systems. Then we go and we lock ourselves away in our office downstairs, and we code and we look at this until we can try to extract information out of it. So we kind of have two groups of telescopes. We have the ground-based ones. So you see here images of the telescopes from the European Southern Observatory. These are located in the northern desert in Chile. On top is the ESO's very creatively named Very Large Telescope, or VLT, which I believe is on the cover of the calendar, which I'll plug in there for you. So each of these telescopes has an 8-meter in diameter mirror. And the building itself it's a few stories high. And then on the bottom we have ALMA, which is a kind of a different type of telescope. It's an interferometer, which basically collects light across a big range of area and kind of mixes or brings these different components together to form an image. And again, to give a scale of how big these things are, European Southern Observatory is currently building their ELT, again, extremely creative name, called the Extremely Large Telescope, and that is it to scale with the Spire in Dublin. And this will have a 39-meter telescope, which is an enormous difference to go from our currently largest one, which are 8 meters, to a 39-meter, which is the technical engineering feats going on. This is incredible. But those are some of the ground-based telescopes. But then we also have the space-based ones, which I'm sure some of these you're probably familiar with. Of course, Hubble. A lot of people know that one. And then its successor, the James Webb Telescope, which has revolutionized a lot of the things we look at. Just that image of the jet I showed you being an example, because the detail you can see is incredible. But then particularly in protoplanetary disks, the Spitzer Space Telescope was also a very important one. And yeah, the reason we have these two different sets of telescopes is, well, because astronomy is a multi-wavelength approach, and what that means is we try and look at these objects through light that we can't see with our eyes. So our eyes are only sensitive to light of a certain wavelength. That's typically the visual wavelengths. But these telescopes are designed to look in different regions and different parts of different wavelengths that we can't detect with our eyes. And that's important because the different wavelengths basically tell you a different story about what you're looking at, because different sources of energy or different types of radiation are emitted in these different wavelengths. And it's only once you kind of combine everything together that you really get a full picture of what's going on. So a nice way to think about it is in an orchestra, the visible wavelength, so those that we can see with our eyes, is one instrument. So you might be your violin, but you don't get the full music unless you take into account all the other instruments, all the other wavelengths, and that plays a key role in understanding all of what's going on in a system, which is what we try to do. So here, this is just an example. The Hubble Space Telescope, all pretty much focused on the visual range of wavelengths, the UV and infrared, and that's the light, the width we can see with our eyes generally. Within protoplanetary disk, go back to our field, my field of research, we typically tend to focus most of it on the ultraviolet to the near infrared or the millimeter wavelengths. But that being said, as I say, it emits in all forms, and it's only once we combine them all we really get a full appreciation of what's going on. And I think this is a really nice. All right, another question. Did Christian Ginsky and his team in Galway witness the formation of a protoplanetary disk this year? Yes. So if I know the paper that you were talking about, I know there was an article in the Irish Times about Christian Ginsky, who's a brilliant astrophysicist in the University of Galway, and they were quite. His detection was not actually of a protoplanetary disk forming, but what we believe to be the second case, what could be the next case of a planet forming in a disk. So a good few slides ago, I showed you the PDS-70 system, which is the first confirmed detection of a planet in a disk. Christian Ginsky and his team in Galway, they now believe they found the next version of that, where we see a planet forming in a disk, which is quite important. So it's not quite the disk forming itself, but it's another planet forming in the disk. But yeah, so going back to this multi-wavelength approach, or this orchestra of instruments in astronomy, this I think is a nice visual to illustrate what I mean by that. So this array of images are all taken of the same star and disk, but in the different wavelengths. So with these different instruments in astronomy, if you will, and you can clearly see we still have the main components of our fried egg in the middle, the yolk of the star, and the egg white, the disk around it. But really, when you go from image to image with the different wavelengths, you see quite different things, and that's a perfect way of showing what I'm saying about these different wavelengths probing different sources of energy and telling a different story of what's going on in these disks. And I think it's quite a nice visual for that. So that's kind of a bit of an overview of what we do and why we do it. But so the field has come a long way. Like I mentioned, it's around 30 years old, so it's still relatively new. We have learned a lot, but there's still a lot that remains to be answered. So these are some of the open questions that we're still trying to address today. So, as I say, we believe the planets will be forming in these disks. One of the questions, as I said, was, do all these disks make planets? If they don't, why is that not the case? Where in these disks are the planets forming? There's a particular line of research where some people might think that the planets form in situ or in place, or are they forming wider out and moving in closer to the star? And if so, how does that happen? Then again, how these systems move on to this planetary system, like our solar system. There's lots to maybe better understood there. Exactly the complexities of how the star and disk interact with each other is also quite complicated, with all these things of accretion, or these jets, or these dust substructures forming. So how do you explain all the smoky stuff that we can see in the other images? And then there's another one, for example, is where and how is all the mass going? Because if we look at a solar system like our own, we can get a sense of how much all the planets and components weigh, or how much mass we have. But then that doesn't necessarily match up with how much mass we believe in disks. So that this material has to disappear somewhere, and exactly how that happens is another remaining question. So, as I said, quite an active area of research. At the moment, we have the person online mentioned Christian Ginsky. He's one of the researchers in Ireland working on this. We have groups all across Dublin, the different universities as well, and then in Cork as well, and pretty much across the country. So my particular research and what the Star Formation Group here in UCD does is we like to look at the inner regions of these disks, the areas closest to the star at the middle, because this is where a lot of this dynamic interactions happen with the material of the disk and the star, and they're all typically quite a difficult region to study, just because, as I mentioned, these things are really far away, and in the grand scheme of things, they're not that big. So when you zoom in even closer, it's harder to tell what's going on. So the next two slides are just a bit of a summary of my own research and how that tries to answer the questions that were still open questions. So I can be focusing on two projects. The first one I did was on things called dippers, which were not chicken dippers, which is a shame. But yeah, that was an awful pun. Anyway, astronomers aren't known for sense of humor, so we'll go with that. But anyway, what's interesting about these dippers is they're systems of stars and disks, but they show very irregular and very short-term dimmings and fadings when you look at them. So this plot here on the left shows this intensity of light coming from the system versus time, and these dips that you see are very irregular, very unpredictable. They happen on around the timescale of a few days. And there's no kind of pattern that we can see from. And my project was part of the project was to try and understand what's causing these, what's causing this dipping. And what we found is basically what we believe to be the case is that there's this extra cloud or dust structure coming from the disk, being lifted out of the disk and blocking the star. So if you're looking at the system, sometimes you'll see it as it normally is. That's the case when it's up here at around 1. But then, for a few different reasons, this magical cloud of dust, if you will, gets thrown up and blocks the star. So when we see it, we see the intensity, the brightness go down.
Sorry, would that be rather like the structures to see in Saturn's rings, where you get kilometre to 2 kilometre high kind of particles levitating above the rings, and it kind of casts shadows?
Exactly.
The Cassini mission got some very dramatic images of that.
Exactly. So it would be that kind of thing on a different scale.
Bigger scale, yes.
Of course, the stars are bigger, and then you need a lot more material to be lifted to make this much of a dip, basically, what we're seeing. But it's essentially that we have the different theories to how this material is lifted. We have things like winds, magnetic winds that can take charged particles and lift them up. If the disk itself is, let's say, inclined or tilted, when we look at it, that'll kind of, as it rotates, it'll block our vision. That's another way. And there's lots of black magic in the magnetic field.
Especially when the dust is electrostatic anyway, to even stick together to begin to build.
Yeah.
Like planetismals and stuff.
Exactly. Yeah. So it's they're quite interesting because of that. They're a bit of a mess study because they're so unpredictable and they happen at such short timescales. But we were able to learn a few different things about that, which was good. So this kind of project kind of aims to answer part of the question, really what's going on in the center region, how does the star and disk interact with and then what kind of material do we have there. The second project that I've been working on kind of focuses more at the evolutionary side of these objects. So we're looking at the formation process and really kind of based here. So the end of the disk lifetime and kind of going towards the planetary systems. We don't have a very clear picture yet of how that conversion looks, as I mentioned. So what we do for this is we look at different star-forming regions that have different ages, and we try and measure with using statistical methods. So if you have a big sample of stars and disks, we measure certain key properties in each system of a certain age, and then we compare these different ages and try and see, can we connect the dots and connect these snapshots, as I mentioned, to form a theory of how these disks are evolving. So that's my current work at the moment to try and help answer these questions. So that's kind of the end of the first part of the talk about protoplanetary disks.
Can I just ask a question before you move on?
Yeah.
How does the Earth cloud, which is spherical, fit in with the disk formation?
That's a good question, and one of the open ones. So the Earth cloud. We don't know a whole lot about it yet because we don't have a lot of measurements on it, what kind of material that is. But it's a good question. I can't give you an answer really for that one. I'm sure there's various mechanisms for, let's say, the planets gravitationally acting and throwing up material, or interactions outside of our solar system with neighboring stars and systems. But then again, it can also come back to how we see this process. And even if we get to this point where we have a planetary system like our solar system, maybe some of this cloud hasn't fully collapsed yet, and you're still left with an Oort cloud or something like that. So, yeah, it's a very good question. Sorry, I can't give you a better answer.
Right.
Another question. In the cloud, the original cloud.
Yeah.
Does it depend how big that cloud is to get binary stars or more stars increase from that cloud? Or why does that happen?
Well, again, one of the open questions, but which we don't really know for sure. And basically, at the moment, what we think is a bit of a gamble whether you produce one star or multiple stars in this process. And that all comes down to the way it collapses in on itself. And it's probably also down to the kind of material that's there to start with, how it fuses and interacts together to form these first seeds that generates this collapse. All that we know is once that reaches a certain limit, then the collapse happens, and it happens really quick. So trying to observe and study that and to see, can we tell why subsystems have a couple of stars, why some don't, have only one, is the thing. But for sure, the mass of the cloud itself is definitely has a strong impact in it. But exactly the intricacies of that, we're not too sure.
To ask the question in a slightly different way, have we seen any protoplanetary disks around binary star systems or multiple?
Plenty. Yeah.
We have.
We have, and they are also a quite interesting thing because, of course, this now has to interact with two stars, and it depends as well on the separation of the stars. In some cases, these two stars are within this gap or this really inner region if they're very closely bound, but they can be quite separated, and that has a whole different thing.
Thanks.
The differs that you were observing does the variation is it the same for all parts of the spectrum?
No, actually not. So, I mean, the data I was working with is kind of the more the visual, if you will, the kind of infrared and the optical. So, and but yes, you can see variability in longer wavelengths, but it's not necessarily correlated one for one. Like it won't vary in the same way as it does in the start. And the reason for this project that we focus in on the visual is because all the dust grains in the visual is where we see their effect most clearly. So we were kind of looking at that because these kind of images these kind of data that first identified them, they were taken that set of wavelengths, and it's because of the dust that we believe them to occur. So that's why we focus on a wavelength. But it does vary across the spectrum, but in different ways.
That's a question on that. Oh, sorry,
Go ahead.
Is that how you tell it's not the star variability, but the actual dust itself?
Yeah, exactly.
That's the same reason.
Yeah. So, part of it is that, but also, as I mentioned, because of the time scale that these things happen on, as I say, each of these dips can be a couple of days long, and that gives us already a hint that it's the dust from the inner region of the disk, because as the gas and dust circulates or orbits around the star, the inner regions rotate faster than the outer regions. And the star itself rotates, and we know, we can tell using different techniques how fast that star rotates.
It couldn't be that, yeah.
And exactly, and then so once we tell how long the dips take place, we kind of get a sense of where in the disk it's coming from. But these wavelengths generally probe the dust, not the star itself, which is why we believe it to be just.
Right. Thanks.
Yeah, and Terry actually asked the question I was going to ask the Oort cloud, but related to that, I mean, the fact that, okay, we think the Oort cloud, I mean, it may well extend beyond halfway to the next star, let's say Centauri. How discrete then are these clouds when they form? Because obviously, when you look at, maybe the Orion Nebula and you say that there's tons of stars forming here, at some stage, little clumps have to break off. So I take it there's a bit of indiscrete matter in between these clumps, or how? Yeah.
Yeah, exactly. But that also ties into the question about binarity and how because potentially our solar system could be part of a binary system, so two stars that start with each other, and then that actually might explain a bit of the Oort cloud. If these two stars interact with themselves and their disks caused a lifting of material. But yeah, it is tricky and a bit of a muchness. But you can see that the scales that the molecular cloud happens on are massive, and that can go into one protostar, multiple protostars. So, and over time, as the stars themselves develop, they will interact themselves with each other and cause movement. So, yeah, it's it's tricky one.
So moving parts. Yeah.
But yeah.
Yeah. So then, if I take it, 4.6 billion years or 4.6 billion years ago, there was a 20 AU cloud of dust out there. It swirled down at 4.4567, and at the center, 1 million kilometers wide, the sun started to ignite, or at least started to heat up before it ignited 20 million years later. And 100 million years later after that, a Theia planet hit the Earth and caused the Earth and Moon to form. Now, is that 100 million years after the formation, is that included in your survey, or is that after the survey that happens with yourselves?
That would be after the survey, because at this point, we are still seeing these planets form. They haven't fully formed yet. But I believe what you're describing is more after the planets have been formed.
100 million.
Yeah.
Yeah, so you haven't observed any impact, or like a lunar impact onto, or a Theia impact onto any planet? No.
Not yet, no. Because these are typically at maximum 20 million years old. So they haven't got to that point yet.
So,
yeah.
So let you push on to the next.
All right, sorry. So taking a hard left turn. A hard left turn to AirSat-1. So I think you guys have gotten a few talks before about AirSat-1. So I'll do a quick recap if anyone hasn't. So yeah, this is a project I was very lucky to be a part of. Very much a right place, right time kind of thing for me. It's not part of my PhD. But it's something I didn't decide with the group here and some of my friends. So AirSat-1 is the educational Irish research satellite. It was made by staff and students here in UCD in the School of Physics and Engineering. It's a 2U CubeSat, meaning it falls in this category of cube satellites, or CubeSats, which are kind of satellites made up of these kind of like Lego blocks. Each block is a 10 by 10 by 10 centimeter cube. So a 2U CubeSat means we've stacked two of these on top of each other to make one satellite, which is what you can see on the right hand side here. That's AirSat-1. And the point of AirSat-1 was Ireland. We hadn't launched a satellite before, and I suppose one of the main objectives of this was to develop the skills and technical ability to build, test, launch, and operate a satellite successfully. And then also, being the educational Irish research satellite, what we wanted to do was get more kids in schools involved and to kind of promote more STEM, physics and engineering and stuff. But we also had a number of science experiments on board. So on the left-hand side here, you can see AirSat, a scheme of it. You can see it's 22 centimeters by 10 by 10. So we kind of call it a fancy shoebox. Roughly, and I'll just quickly go through some of the science experiments we had on board. So we had EMOD, which stands for the NBio module, which is this kind of black and white checkered merge that you can see on top on the figure on the left and in front of the figure on the right. Basically what that was is the black and white coupons are essentially fancy paint. They're a thermal coating that protects satellites and hardware in space from the harsh space weather, from radiation from the sun. And this was and they were made by a company called Empey Limited, based in Cork. And this was the first time that this material was tested in place. So that was one of our experiments. We also had the GMOD, or the gamma ray module, which is this block here. That was a detector developed and built by the staff and students here in UCD. And what that was, it was a detector for catching and observing gamma ray bursts, which I know Antonio talks all about, and I think Laura talked a bit about here as well. And these gamma ray bursts come from the most, some of the most energetic, most explosions in the universe, which occur either from massive stars dying and exploding, or really other heavy stars colliding in themselves and creating these bursts of energy. And so GMOD aims to try and catch these in real time and to record how bright and how long these things lasted. We also had a software experiment called WBC, or the Wave-Based Control, which was a software experiment that basically was a new way of telling satellite how to orientate itself in space, which is quite important when you want to communicate with it, or if you want to point your solar arrays at the sun to charge it. And then lastly, although not an experiment, but still quite a cool thing, one was the ADM, or the Antenna Deployment Module, which was a new way of basically deploying your antennas that we communicate it with, and it really came down to a very simple mechanism of fishing wire and a resistor, and that was the first time we put in the satellite and worked successfully, thankfully, because we were able to communicate with it. So that was kind of the science purposes of AirSat. So AirSat launched on the 1st of December in 2023 on a SpaceX Falcon 9 rocket. There was the live stream of it, and it was quite a special day for everyone on the team to finally see these years of work come together and to see it go into space. Around 90 minutes after that video was taken, at an altitude of around 519 kilometers, a door opened, and a spring shot AirSat out into space, which you can see happening right. That's an actual video from the deployer, and that little chute is AirSat flying off. And that was the last time anyone saw it with our eyes. 45 minutes after that happened, AirSat 1 turned on, and she started singing. And for the next, for the next year and a half to 2 years, we were communicating with AirSat on a daily basis from here. We have these antennas built just upstairs on the roof of Beach Hill here. We have a set here. We also have a set in a farm, one of our team out in Kerry, all the way in the west. And these antennas tracked AirSat that came above and below the horizon in Ireland. And during these windows that AirSat came above and below the horizon, we had a team of operators, of which I was a part of, communicating with AirSat, sending messages and receiving data from it. And the little image here on the right is kind of what we were looking at a lot of the time, which is these measurements of the satellite's well keeping, so the temperature, battery, how the solar panels are working, the timekeeping, and then also the science data that we were getting down from the satellite. One of the challenges we faced during the mission, there was a few, but one of the main ones from a science point of view was from the gamma ray module, or this gamma ray experiment, which, as I said, was aimed at detecting these big explosions in space. And basically what we found is we had this issue over the South Atlantic anomaly, which you can see here in the blue kind of contours on Earth, where you have a kind of a weakness in the atmosphere, basically, where you have lots of charged particles. And what that did was it made AirSat reset. There was all this influx of particles, and that made AirSat reset, and that caused problems. We had to then set it all up again, and then we weren't able to detect these gamma ray bursts if they happened. So what we had to do, we had to develop a method of basically using its location on Earth and turning it on and off as soon as it crossed, turning it off as soon as it crossed this region, and turn it on again once it passed this region to protect the satellite.
Those contour lines in the anomaly, are they what, microtesla, or what are they? But what is the actual variation in sort of the strength of the magnetic field there compared with the average? Is it percentages? 20%?
I have to for one of my teammates for that one, and it's basically a weakness in the atmosphere.
I know, but what would be the weakness?
I couldn't, to put a number on the percentage, I couldn't tell you. But in terms of charged particles we were receiving, if we were not getting any kind of GRBs or gamma ray bursts, we would get, like, as a background, let's say 35 to 40 counts per second. But in this region, we were getting up to a few thousand per second. So that's how much of a difference there was. And that's what we had to turn off during that time. So the exact measurement, I don't know off the top of my head. But yeah. And then on the 4th of September this year, AirSat came home. AirSat 1 didn't have any thrusters on board given its size. So the lifetime of AirSat was purely based on how long it takes for it to fall into Earth from the altitude of 519 kilometers that it was deployed at. And unfortunately, due to the solar weather that we had this year, it came down quite a bit faster than we had thought it would. So sometime between 3:24 and 4:06 p.m. Above the Pacific Ocean, AirSat 1 entered Earth's atmosphere, entered low of Earth's atmosphere and burnt up over the Pacific Ocean after around 10,000 trips around the Earth. So the image here on the right is some of the team communicating with it for the very last time in the operations room downstairs. So I kind of just wanted, so in terms of the outcomes of the mission, as I said, given it being the educational Irish research satellite and our goal of developing the technical skills and ability to build, operate, and launch a satellite. This was quite successful. This is a picture of some of the team that was involved. We had over 50 staff and students involved from start to finish in the project. And then from the lessons learned from AirSat, we have other satellite projects currently ongoing. That'll be the next generation of Irish spacecraft, which is great. But we also had lots and lots of outreach, lots of school talks and workshops with kids across the country, interviews and radio stations and all that, to get a lot of people involved in on this. So it was a good success from that point of view. But also from the science point of view, we did get some valuable data, which is still being analysed, still being published as papers. Here is 2 examples of 2 gamma ray bursts that were caught by AirSat, by GMOD. These peaks here is the detection of those, and basically whenever we caught a gamma ray burst, we caught around 12 during the lifetime, the team would send out a notification to the whole community that we had seen one, and then they would point their telescopes and their information at it to try and follow it up and try to study more about it. So we had 12 of those in total, and there's still papers being written about the data on that. So that's a bit of an example. And so just before I finish, I wanted to end with some of the messages that AirSat left us as they were going down. So AirSat was transmitting data all the time. And I have a few screenshots of some of the quotes and messages that AirSat left as it was falling into Earth. So one of them was the poem. So AirSat 1 had a poem inscribed on the bottom, which was developed or was written by kids across the country in different schools. They all had to write a line of a poem with a theme of home. And using the UCD Department of Literature, a poem was created from all these lines, and it was inscribed on the bottom of the satellite that pointed towards Earth, so it was always pointing home. And so we transmitted all the lines of the poem in the final days that AirSat was in space. If you haven't heard the poem, I would recommend. It's called Always Home. You can look it up on, there's a beautiful animation with it as well on YouTube. So that was one quote. We had one from Amelia Earhart saying the most effective way to do it is to do it. So these are all screenshots taken from Twitter of people who around the world who were able to detect or pick up these last signals from AirSat. We also had Oscar Wilde saying we're all in the gutter, but some of us are looking at the stars, which was quite a nice one. And then very lastly, its final messages before burning up and crashing into the Pacific, or sorry, not crashing, it burnt up, didn't reach the Pacific, was Schlango fall. So, yeah, I'd like to end on that. I hope I haven't taken too much of your time.